Welcome to this lecture series in group theory. In this lecture, we look at a certain special kind of action of a given group on the set of all the left cosets of a given subgroup, which we will call the coset action. And let us recall some relevant material. So given an action of a group G on a set X, we defined the kernel of the action as those elements of G, those elements of capital G, which fix everything in the set that we are acting on. So that was the definition of the kernel of the action, and this was same as the kernel of the group homomorphism that we obtained out of the action. So we defined action in two ways. One definition of action was you take a group and take a group homomorphism into the symmetric group of a set, and that is the notion of G acting on X. And there was this other notion. So first we recalled the definition of kernel with respect to the other notion, but it is same as the kernel of a group homomorphism. All right. So in particular, this thing is a normal subgroup of the group G. Although you could have checked that directly, but from here it's immediately clear because kernels of group homomorphisms are always normal subgroups. Here are three problems for practice. And now let us get to the material of this lecture. So suppose we have a group G and we are given a subgroup of it. Then recall that G mod H denotes the set of all the left cosets. Left cosets of H in G. So thus G mod H is nothing but, this is nothing but this set, right? And now finally we come to the important definition. We define an action of G on the set of all the left cosets of H, as we will do that, but let me emphasize that when we write G mod H, we do not mean that H is a normal subgroup or anything, or that this is the quotient group or any such thing. It is just the collection of all the left cosets. In case H is a normal subgroup, that collection of left cosets naturally becomes a group under a certain product that we have discussed. But if it is not a normal subgroup, this is just a set. There is no group structure on it. All right, now we will define an action of G on this guy as follows. So define a map capital Phi from G cross G mod H to G mod H as follows. It takes an element little g, comma, a coset to this coset. So that is our map Phi, but we need to talk about well-definedness because a single coset may have many representatives. So we need to say a few words about well-definedness. It's very clear. There's nothing very difficult about it, but let's do it. So Phi is well-defined. What do we need to show? We need to show that let G be in the group and xh equals to yh for some x and y in the group G. So suppose we have a coset of H, but it can be expressed in two different ways. Want to show that phi G comma xh equals phi G comma yh. This is what we want to do. This is what well-definedness means. But what is this? The left-hand side is this, and the right-hand side is that, which is to show that this is the case, right? Which is to show that this is the case, which is to show that this is the case, which is to show that this is the case, but that is the case. That is the assumption that we start with. So well-definedness is clear. All right, and I'll leave you to check that this is an action. So check that phi is an action of G on G mod H. All right, also note that this is a generalization of the regular action. If you take H as the trivial subgroup, meaning this subgroup, then this thing is just the regular action. Essentially, you just have a little decoration here. That's the only difference. All right. So we will prove 4 things about this action, and that will be for this lecture. In the next lecture, we'll look at some applications of this particular action. So suppose H is a subgroup of G, and consider the coset action of G on G mod H, and let N be the kernel of this action. So then, first of all, we will figure out what the kernel is exactly. So this is our first statement. Let's do this. So as we saw, X is in, not X, G is in the kernel of the action. So I'll just write ker to denote the kernel of the action. So this happens if and only if G fixes everything in G mod H, which is to say that G dot XH equals, if and only if G dot XH equals XH for all X in G, right? G is in the kernel if and only if it fixes every element of G mod H. So an arbitrary element of G mod H looks like this, and that's what this means. So this is same as GXH equals XH for all X in G, which happens if and only if, all right, so it happens if and only if this is the case for all X in G, which happens if and only if this guy is in the subgroup H for all X in G, which happens if and only if G belongs to XH X inverse for all X in G, which happens if and only if G is in the intersection of all these conjugates of the subgroup H. So from this equivalence, G is in the kernel if and only if G is here. It just means that kernel of the action is equal to this thing. And we have proved our result. So this proves what we stated here. And since N is the kernel of our action, N is in particular a normal subgroup of G. In fact, it is the largest normal subgroup of G which is contained in H. So we will show that the kernel of the action is the largest normal subgroup of G which is contained in H. And let me make that maybe more clear. So want to show that 2 things. First is that N is normal in G and that N is contained in H. Whether you write this symbol or that symbol, it's the same thing because both are subgroups. So I choose to write that symbol. And second, we want to show that if K is normal in G and K is contained in H, then K is contained in N. So first statement says that N is a normal subgroup of G which contains H, which is contained in H. And the second says that if you have some normal subgroup of G which is contained in H, then that normal subgroup is actually contained in N. So it is in this sense that N is the largest normal subgroup of G contained in H. So this part is clear because N is the kernel of the action, and in particular, it is, all kernels of group actions are normal subgroups of the group in question, and therefore that normality is clear. This is also clear because what is N? This is clear because N is what? We saw that N is this guy. Maybe I'll shift it a little bit. XH X inverse, which is contained in H. Because if you take X as identity, you'll see H here, and since it is an intersection, it contains everything that you see here. In particular, it is contained in everything that you see here. In particular, it is contained in H. So just by the description of N that we figured out in the previous part, we have this deduction. Now we want to do this. So suppose or assume, so let K be a normal subgroup of G such that K is contained in H. Want to show that K is contained in N, but we have, since K is contained in H, XK X inverse is contained in XH X inverse for all X in G. But since K is normal, this is equal to K, and hence K is contained in XH X inverse for all X in G, and hence K is contained in the intersection of that. There's no for all now, which is equal to N. So that's the proof. That finishes the proof of B part, and therefore we have proven part 2. that n is the largest normal subgroup of G which is contained in H. Now we have two more things, but they are quite related, so let's prove them in one shot. If H had finite index in G, meaning if this was a finite set, then N is also a finite index subgroup of the group G. And more strongly, we will show that the index divides this finite number. So let's do this. So we have a homomorphism. Phi G going to the symmetric group of G mod H. Where do we get this homomorphism from? From the action. G acts on G mod H, so we get this homomorphism. And since N is the kernel, we get, let me make the diagram. So we have a group homomorphism, and it will factor through the kernel, factor through the cosets of the kernel. This is the natural projection, takes G to Gn. And this is phi bar, it's an injective group homomorphism. All right, thus phi bar G mod n is a subgroup of this thing. So if this is finite, is let's say some number n, which is finite. This is the notation for finite. If you say some quantity is less than infinite, it just means that it is finite, nothing more complicated or interesting than that. So if H had finite index in G, and if the index is denoted by the letter n, then by Lagrange, we have the cardinality of phi bar G mod n divides the cardinality of symmetric group of G mod n, which is n factorial, because G mod H has size n. And since phi bar is injective, this left hand side is nothing but this. So these two things are equal. Divides n factorial. And this means that the index of n in G is finite, and in particular, or rather more strongly, it divides the cardinality of this guy, which is nothing but the factorial of the index of H. So we have proven both the parts in one shot. Basically, the third part is only the fact that this is a finite thing, this is an injective map, and hence since you're embedding some object into a finite set, this object must also be finite. And the second part was the divisibility claim that immediately follows now from Lagrange's theorem. So that's it. That's all for this lecture. Next lecture, we'll see some applications of this Coset action. All right. Thank you for listening.